Hello guys, welcome to another LeetCode problem coding session. In this session, we'll solve serialize and deserialize binary tree, LeetCode number 297. It's a hard problem in LeetCode. We are actually solving the blind 75 LeetCode questions, and we are in the tree section. And this is the problem we are solving, serialize and deserialize binary tree. This problem is a little bit interesting problem to me because I was asked to solve this problem in real interview multiple times, and first time was in 2013. The problem is hard when you try to do the both serialize and deserialize, because then it might be a little bit difficult to implement the whole part if you are not careful enough. So let's jump in. So we are given a binary tree. So let's draw this binary tree and I'll talk about in detail here. So we have a binary tree like 1, 2, and then 3, 4, and 5. So when you are serializing a tree, the basic thing you are given a tree structure, and the output needs to be a string. So basically, you want to transfer this data from one machine to another machine, and you can't just send data as an object. You need to convert it some sort of string format for easy transfer. So if you want to serialize these one, few key things to keep in mind, right? So if it's a binary tree, all the node has left and right node. And for example, if you take a look at the 2, right? So 2 doesn't have anything, right? The left subtree and right subtree are none for the case of 2. Same as for 4 and 5. So serializing is not that hard because you can specify easily how you want to serialize this tree. The main interesting part when you want to deserialize, right? Because you need to use the same sort of algorithm how you serialize it so that you can reconstruct the whole tree later, right? So for this problem, how we will solve it? What we will do, we will basically, for each of the null node, we add an X to the result, right? So let's see what are the null node here, right? So 2 has a null node X, right? Left and right? Same as for 4 and 5, right? So when you're trying to serialize this tree, what we can do, we can have node 1 value like 1. Then one had left tree and left node and right node, which are 2 and 3, right? Now, when you are doing 2, then 2 has same as left and right, which are both are null. So we'll just put X here. Now we'll look into the left-hand subtree for 3. 3 has 4 and 5. And then there'll be left and right for both 4 and 5. So if we can do that, the interesting part is that actually for each of the locations, so for if you representing as a list, right? So 0, 1, 2, 3. So there is an interesting thing we can see with the indexes, right? So main interesting thing is that, so let's do this one. So the left node and right node of 1, these are the 2. So these one and these one, right? And what about 2? 2 has this one and this one. This will be really important when you try to deserialize this part. And for same as like 3 locations. So 3 has left and right subnode is here and here. So let's go ahead and implement this one. So the first part is not that much hard, the serialize part. So what we will do actually, if this root is null, we'll just return an empty string. We will use a queue to traverse the whole tree, same as like BFS structure, how you actually traverse level by level, so that you know actually when you are encountering the left subtree and right subtree. At first, we will just append the root node here. And then let's take a list with data, which will be a list of all the items what we have in our binary tree. And while we have this DQ, we will basically pop one of them, each node. And if it is a null node, then we basically want to add a X into the list. And for this part, actually, when you are done with the whole thing, you will just get out of this while loop. Otherwise, you just append the value of this node n dot val, and then you just basically dq dot append the left and right subtree. So n dot left. So this problem is quite similar to the BFS, what we implemented, or level or traversal we implemented in another video. I will add that to the description. Then only difference is that if it's a null node, we are still adding to the this queue, because we want to make sure for each null node we add an X. In that algorithm, we haven't used that one. We previously check if it is not null, then actually we are adding it. And finally, what you want to do when we are outside of this one, if we want to convert it as a string from this data list, right? So we can convert based using a comma. And we'll do joint of all the data, right? And you can just return this data str. And just to show you guys what does it look like, so I'll just print this one and we'll see how it's look like. So if you hit the run button, you'll be able to see how does it look like in the std out, right? So our final string looks like this 1, 2, 3. So if you just make it a little bit, so this is our final output, right? So 1, 2, 3, you see here std out 1, 2, 3, xx 4, 5, xx, xx. So this is the final, we are sending it back. So how we can reconstruct the tree in the deserialize part, that's the most important part, right? So when we are trying to deserialize it, let's do the same thing, but in a reverse order, right? We need to make sure we can figure out actually which node will go to the left node and right node. So we are given a data string. So if it's not data, we'll just return a null node, because if the string is empty, we basically return a null node. Other than that, we will actually create a list. We will just split it based on the comma. So you see, let me show you the test result again, right? Test case. So you'll see in our std out, we have these one, right? So if you want to reconstruct the whole tree, we basically want to split it out like 1, 2, 3, right? So we are splitting based on these comma. So we'll get the list back, whatever we did it. So this is the reverse part we are doing. So we are creating the list first, right? Now let's go into detail. So for each of them, how can we do that? So we have the list in DL, which is basically data of list. We'll create a root node, and the root node is basically a tree node. and the tree node would be int of DL of 0. So what would be the root node? For our tree, you see actually 1 would be the root node, right? So if we go into here and just mark this one, so these will be our root node. So we create this root node first. This is our root node. And then we will, previously we created a DQ, which actually store all the nodes. So here you can use DQ or you can just use any of the list, because we don't need to traverse the whole thing. So if our list is node queue, and for node queue, we basically append the root. Now, what you want to do we have so basically we created a root node for here. So from this root node, we reconstruct this one. So how can we get the left and right subtree, right? So that's what we need to figure out. We already traversed 0, so we will start from this location using a for loop. So if you write for I in range, start with 1, and you basically go to len of DL, the whole list. So we have to define another node, and we want to pick up the value from just look at it. So for when we are starting, I is equal to 1, right? Here, when we are here, I is equal to 1. So we'll get the value from the node queue, what you already appended. So it's in our node queue, and what we will do, we will do I minus 1 divided by 2. So we'll do an integer division. So what basically we are doing, we are picking up this P node. So in this line, you see we append this root node into our list of node queue. We basically get that node and try to find out actually what would be the left and right subnode for this one, right? So, and then at first we are assuming n is none, and I will explain why. And then what you will do, you will check actually if the location of I, which is equals to an x. If it's not in x, for example, for the case of 2, right? So 2 is not an x. That means actually we need to create this node, this 2 node, right? So we got the 2 here. We got the 2 here. It's not an x. We create this node, and we create this node using like n equal 3 node of int of dl of I, right? So we create the node, and we append this node to our node queue again, because next time what we need to do, we need to create a left and right node for this specific node. And now what you want to do, if you want to check actually which location are you in right now. So if your index is divisible by 2, then you do something, otherwise you do the other thing. So I'll explain what does that mean. That actually comes to the other part. Finally, we return the root. So what do you do here? So I was 1. So if I was 1, then at first we want to get the node queue I minus 1 by 0, right? So in our node queue, we keep track of all the node we added, right? So at first in the node queue list, we added the tree node of 1, right? So this is our tree node. So when I equal to 1, we are I minus 1 divided by 0. So this becomes 0, right? So you basically pick up this value from there. So your P becomes a node which contains 1, which is basically your root node. Now you want to find out actually for this root node. I'll just remove this guy so that it's easy to understand. So this part. So you got this value p, which is 1. Now you are checking if I equal to 1, what is the value inside your list? And your list, you get the 2 here. So if you get a 2, which is not an x, so you want to create a tree node. So basically, we are creating a tree node again, right? Which is inside the n for now. And next, we are checking I is divisible by 2 or not. So if it's not divisible by 2, that means modulus is 1. We basically want to put the p dot left node as an n, right? So what we are trying to do, p dot left is equal to this guy. What will happen when I go to 2? If I go to 2, then you got the same value p equal to 1 for the first case here. You pick n equal to none. It's not in x because it's in 3 here. And then it's not, you create another node like 3. And since it's divisible by 2, you basically add it as a right node. So that's how actually you create all the values. So basically you are going through one item in this list at a time, create a tree node, either a none or actually a tree node, and then put it to the left or right node as a sub node for the previous node what you already encountered, right? Next thing, what will happen actually when you encounter this first x, right? So when you encounter this first x, you basically, it's in 3 and 4 location. So you 3 minus 1, so you calculate this value 3 minus 1 divided by 2, which will give you actually 1. So that means the parent of these 3 and 4 basically located in location 1, right? So that the red 2 sign you need to remember, right? So when you created X none node, you basically go to the left node of this 2 and also these 2. Same for 3 and 4, you will get actually 4 here and then 5 here. And finally, you return the root. And so we can comment out this one and try submitting. So len is not defined. So let's fix that. This will be a len. And let's see if there is any other problem. So it looks good. So let's submit it. Okay, everything looks good here. So let's talk about the runtime complexity for this problem. So for the serialization part, so you are given a tree of n node. So, and you are using DQ, right? So it's a queue. So this will be the serialization part is order n because you're traversing all the node and you need a size of all the node, right? So this is the runtime complexity and space complexity for the serialization. For the deserialize part, at first we are splitting this one, same thing. So we are going through the list only once. So these will be basically order of n, whatever the number of elements you have. And basically it will be a order of n, a little bit more than n because you have some null node there, right? So, but not more than 2n, right? So each of the node might have actually 2 null node. So although we have a 1, 2, 3, 4, 5, there are 5 nodes. But basically, when you look into the list size, it will be for each node, it can have a left and right sub node, right? So at max. So 2x null node. So you can see 5, 6, 7, 8, 9, 10, 11, right? So total 11. So all number of node will be actually bound by 3n, right, at max. And we are using a node queue, which will be an order n data structure. So we are storing all the value in the node. That's pretty much it. Actually, we are not using any other extra space. So this is also a order n runtime and also order n space complexity. That's pretty much it. So thanks for watching. If you are new to this channel and preparing for technical interview, consider subscribing. And if you have any confusion about the algorithm or actually runtime complexity or space complexity, you can write into the comment section. I'll see you in the next video.